Okay, so I'm happy to introduce our next speaker. This is Emily Gorcenski from Thoughtworks. She's the data scientist there. And yes, please welcome her for this next talk. Thanks.
Cool, thank you very much. So I want to talk today about doing continuous delivery in a machine learning context. I'm going to make some assumptions here, and to be kind of honest with you, I've given this talk a lot lately, and I'm going to try something completely different this time, and I want to spice it up a little bit and get technical. So I'm going to actually cut the presentation part short and just try to throw some code around, specifically around how to break a machine learning application and then how to unbreak it within the same patterns, workflows, practices that we use in software engineering. So I'll assume that you're all familiar with continuous delivery. If you're not, raise your hand now. It's okay if you're not. Okay, just a couple people. Basically, continuous delivery is this concept where you want to be deploying and releasing multiple times a day, ideally at least once a day, and have your software in a state where you can roll forward or roll back very easily. And there's lots of things that go along with that, but I won't talk a lot about that. I'm from Thoughtworks. We're pretty cool. We're over by Checkpoint Charlie and all over Germany and also all over the world. One of the things that we publish is the technology radar. And I call this out because what I'm talking about today, continuous delivery for machine learning, we've put it on the technology radar under trial, which is a very big deal. And the reason that we talk about this as a specific topic separate from continuous delivery for software is because what we're seeing at clients and in the industry and talking with people at conferences is that machine learning is hard, and the patterns and practices that work for software do not necessarily work for machine learning. And we see lots of patterns and things like that with how data scientists are organized in teams versus not organized in teams, what their work artifacts are, how frequently they get used, things like that. So we've made this a special topic. So just briefly, principles of continuous delivery. I put this up here because this book is hitting its 10th anniversary. This was the foundational book on continuous delivery. And I won't go through this, but one of the things that we talk about here is building quality in when we develop and keeping everything in source control. And those are two things that are very difficult in data science. And actually, I think that I'd have to talk to Jez. He's a former thought worker. But if you actually read this book and you look at the section on data, it's like one chapter and it mostly talks about databases. So it's time for an update because machine learning well, there's a lot of stuff going on and nobody's really sure what the right way to do it is. So productionizing machine learning is hard. We want to do continuous delivery in a way that is reproducible and testable. We want our software to be auditable, and we want to be continuously improving. If we implement an AI system or a machine learning system or a data-driven system or whatever you want to call it, depending on which level in the organizational hierarchy you're talking to, machine learning breaks these things because it is non-deterministic by nature. It's all built on probability and magic. It's hard to test, and because of this sort of black box approach, it's very hard to explain. We don't know why a system is saying, I think you should buy these socks. We just know that it is. And because of that, if we get some aberrant behavior or if we want to improve it, it's very difficult to patch. And it's very difficult to improve because we don't know. You could make a change over here, and that has a ripple effect that affects things way over there. So if it's hard, why even bother with continuous delivery for machine learning? Why bother doing this at all? And that's because machine learning models have a shelf life. Your data goes stale, your models go stale, your customers grow and evolve, your markets grow and evolve. And if it takes you 14 or 16 months to put a single machine learning model out into production, that's probably stale by the time you get it there. So we want to be able to iterate more rapidly. We want to be able to move our data scientists' work into production faster because data scientists are very expensive. Trust me, I know. I am one. And we don't want their work to be sitting on a table or in a laptop on a table somewhere or even on the cloud. We want it to be in production. So if we think about how an AI system can change, there's a few different ways. We can think about code changing in the normal way. If we build a service, we write code, we fix a feature, great. But if you think of a machine learning model, it's data combined with a modeling approach in this case, like a neural network or a random forest, and then some code that implements that. So let's just briefly walk through how code changes versions. And then what I'm actually going to do at the end of this is walk through a real machine learning application. Well, not a real machine learning application. It uses machine learning. But it's a toy application. And I'm going to break it in many ways to show you how pernicious these problems can be. So we're familiar with how code changes version. Maybe it's a bug fix, a new feature, we upgrade a security patch or an operating system, or we change scopes, whatever. That's usual. Our model can also change. It can refer to the modeling approach, but also the actual artifact that is produced in our machine learning process, meaning the pickle file or the PMML file or whatever it is that we're creating. And that model is a product of both the hyperparameters, which are not changed during training, and parameters which are computed during the training process. So why would we change a model? Well, maybe we're trying a different approach. Maybe we think that the neural network gives us too many unforeseeable difficulties, and maybe our customer service is getting too many calls being like, why are you recommending to my 85-year-old grandfather that he should be buying this CD? Clearly, nobody has a CD player anymore. Maybe you have new dependencies or new data, or you want to improve your performance. So a model can change, and it should change, because that's what you pay data scientists to do. But when it comes to actually looking at data, things are much more complicated. And this is the sort of sticky wicket in machine learning. We can decompose data into two things. We can look at it in terms of sampling, which is the actual values that the data takes, and we can look at it in terms of a schema, or the shape of the data, which could be the columns, their data types, how they're computed, things like that. So sampling changes normally. So if we think of a model as a description of our universe, data is a measurement of the universe at a point in time. And as we move forward in time, our data changes. We get new customers, they buy more things, or they return more things, or they quit, whatever it is. The distributions of our data can and should change over time. So the fundamental assumptions that we make over how our data looks in a probability space should not stay the same as time moves forward. And schemas also change. We live in a world where we're integrating many third-party services, and they love to change things and not tell us. So all of a sudden, you get a JSON payload that has a bunch of extra fields, and you're like, what is this? Or even worse, the fields are gone, and then everything breaks, and then you have to call them up and be like, what happened to those fields? So these things can also break. So if we think about a machine learning system as having 4 different version axes, we can start to conceptualize the challenge of doing machine learning in a continuous delivery way, because each of these things can drift independently or concurrently, which makes the challenge of doing machine learning in a continuous delivery sense sort of 3 orders of magnitude bigger than just standard deterministic software engineering. So let's talk about what we would need in a full stack. If we wanted to build a full stack, well, first we need to start with discoverable and accessible data. This is not as easy as it might seem, but if your data scientist can't get access to the data, you're pretty much stuck there. And so this could also be seen as a data governance layer, or just a data migration to a data lake, or whatever it might be that you need. We need version control and artifact repositories, because we need to be able to handle data that changes and to be able to reproduce our training results at any given point in time. We need a continuous delivery tool. Doesn't matter which one you pick, but it should be able to combine pipelines, because we want to separate our machine learning training process from our build process for our integrating services. In the perfect world, we'll have an infrastructure that can run multiple environments and experiments, because some of the best machine learning companies will run multiple shadow models. So instead of like a staging environment, they'll have multiple, or think more in terms of like blue-green testing. They'll have like blue, green, red, whatever, many colors of the rainbow, which I'm wearing in my skirt today. We also want to be able to track the performance of our model both in production and during the research stage. So we should have performance assessment tracking tools stood up. And sort of concurrently or hand in hand with that, we need model monitoring and observability because we want to be able to capture the results before they create unseen difficulties in our data so that we can capture the challenges sort of in real time. So I do want to walk through an example, and I have no idea if this is going to work because I don't know, but we'll give it a try. We put together a toy problem based on an actual client that was also became a Kaggle competition. What we wanted to do was predict the number of items that would sell because we were trying to build an application for their purchasing team so that they knew how many items to buy ahead of time based on the last 4.5 years worth of data. So we were looking at 125 million transactions across 50 stores. This was in Ecuador. And I think there was something like 4,000 items in this data set, and those items changed over time as well. So we wanted to predict how many of each product will be purchased for a given store on a given date in the future. So yeah, let's give this a shot. I know that I can get the machine learning part of it working, but I was wrestling with the infrastructure because who isn't terraforming things right before you give a talk? So we'll see if it works. If not, we'll just break some applications. Aha, it does. So let's have our nifty little sales forecasting app, right? So let's say that we wanted to know how much milk we needed next week, June 27th. Well, that's a request failed. Let me try restarting this application. Ah, yes. I should relaunch my application after making these changes. Okay, sorry about that. So let's say, no. There we go. Computers. Aha, I've defeated computers. So let's say we want to know how much milk we want to buy. Well, it's saying 3 milks. That doesn't seem exactly right. We know that this store is going to sell more than 3 milks on June 27th. So maybe we say, all right, our model is not so good. We need to make some updates to it. So fortunately, what we've done is we have put together a handy little tool, model building tool. So let's say that we're using a decision tree to make our predictions. And now what we want to do is use a random forest, right? And so we're going to do that, and we're going to retrain our model. It's really hard to type while holding a microphone, by the way. No, it's fine. So one of the tools that I like using when talking about version control for machine learning is this tool called DVC. DVC is a nice little tool that does 2 things very well. One is it versions data and stores it in the cloud, and then creates a little manifest file that you can then put in your Git repository, which is great. The second thing that it does is it allows you to build pipelines. And so if you have a complex process of taking apart your data into training and validation sets, and like you have to do multiple steps, rather than putting things together in a shell script, it allows you to chain things together in pipelines, and it's smart enough to only rerun the stages of the pipeline that change when you change a script. There's some other tools that do this, like Pachyderm does this, and MLflow, I think, has this capability. Probably like 50 more tools out there that I don't know what they are, but I use DVC. So what are we doing? We've rerun a model, and we've said, okay, what I really want is to minimize this NWRMSLE metric, because that's what we've been told to minimize. And I think it stands for normalized, weighted, ratatouille, mean, least squares. I don't know. I have no idea what that stands for. All I know is that smaller is better. So 0.74 is what we've got when we switched to a random forest model, and we had like a 0.8 something before. And our statisticians have told us you need to get that number under 0.8, and so that's good. We did. So I'm going to do this, and I'm going to commit everything. That's probably pretty small. Let me make this bigger. There we go. Somebody should yell at me if it's too small. So let's just commit this to Git. This is really hard to do with one hand. Oh no, don't push that way. Oh, don't push that repo, that's okay. Thanks. All right, so what we want to do is commit these changes because things are good, right? One of the things that we get with statistics is oftentimes the thresholds for acceptance are just kind of made up. That's kind of like the second law of data science, is that no matter how sophisticated your statistical analysis is, a statistician will always pull a magic number out of thin air and say, this is right. So we've committed that. Now, everything is happy. So if we go back to our terminal here and we restart our application, just running everything locally, we should see some better results for milk on the 27th. Great, so 31 milks. That sounds a lot better. I'll make this bigger so you can all see this lovely purchasing app. Wouldn't you be excited? I'm sure that Zalando has a better one than this. All right, that's all well and good. But then someone comes along and our app developers are like, oh, look at these data that we have. Please don't copy this code. This code is not production quality. It's just an example. Our app developers are like, yeah, did you know that we've got these hard-coded values that are sitting around in our production code? Well, that's bad. So we're going to just ignore those, right? And take them out and refactor our application. And so now we relaunch the application, and we want to go predict our milk again. And then everything's broken because we've taken fields out, and our system is not robust to that. So now we go back to our machine learning engineers, or our data scientists, and say, hey, we broke the model. And can you retrain it without these fields? And then the data scientists are like, are you kidding me? Sure, of course I can retrain that. So then they'll come through and they'll be like, okay, well, backend engineers are not using this data, so I guess I'll just take this data out and I'll just filter it out of the database when I do my training and my validation. So then we can do this. We can do a reproduce again and retrain our model to see how our scores get. And this will take a second. So in the meanwhile, what I'm going to do is build our fancy CD pipeline. Because what we like to do is we like to use GoCD at Thoughtworks because we built it. But anyways, we have built a CI/CD tool that can actually integrate all of these changes and do the training. We can kick off these training jobs in the cloud and run integration, acceptance, and even unit tests on the machine learning model, and then automatically have a build and deployment pipeline. So I just have to make some changes here. I wanted to get this done beforehand, but Terraform was not agreeing with me. So we'll just add a pipeline here. If you don't know what I'm doing here, that's fine. I can walk you through GoCD anytime you want, but I'm going to do this live because I want to show you how easy it can be to do this. I'm sorry?
With one-handed.
One-handed. I'm doing this one-hand type. Well, it'd be very hard to also hold the microphone if this was tied behind my back. I mean, we've done a lot of work on this workshop thingy to make it easy to do this. See, we have our workshop app building now, and now we're just going to connect the pipelines. And that should be good. And then what I want to do is change this to use DVC. Hopefully it will work. And there's a magic command that I have to copy paste. because I never remember what it is. Okay. So if all of this works, I'll have live built a continuous delivery for machine learning pipeline in 20 minutes while on stage. 5 minutes left. Thank you. Okay. I don't know what's happening there. Let's try this again. Custom command. Cool. All right, there we go. So all this should be working, and if I unpause this and play it, it should actually build the machine learning pipeline that I've run. Yeah, so back to the training now that our machine learning has done. One of the things you have to be very good at as a data scientist is either procrastinating or multitasking, because training takes so long. When we've taken out these two fields, our score has gone to 0.81. So the fields that were being hard-coded in the back end have now, we've removed those hard-coded fields, but now it's broken our model, right? And so we're like, why should that make any difference? Well, who knows, because it's machine learning. But what that tells us is now we have to do iteration. We have to do some more research to figure out how to actually get our score there. And so that gets to the point where we need to start getting things set up with our research pipeline and having a pipeline that supports us for trying different models, tracking their performance. If I had a little bit more time, I'd also get MLflow set up for you. But yeah, so that's the basic gist of it. Given that I have only a couple of minutes left, I'd be happy to walk you through this offline after the last talk, but I'll be thrilled to take any questions that you might have now.
So first, a round of applause for Emily's talk. I just want to recognize the courage it takes to do all that live. One hand in the microphone, one hand typing, so really well done.
I almost got it, but I forgot to commit one of the files. So that was my fault. Otherwise, it would have been great. So we
have time for a few questions. So yes? Okay, who? I see you have a question. Okay. This way? Yeah. Okay.
Thank you. Hi, thanks for the one-handed demo. That was awesome. I wanted to ask about ideas around observability of how, when models ran and which versions and how they performed, if you have any ideas on that or any cases that you've seen.
Yeah, so what we do, so what I just gave you was the literally 15-minute version of a workshop that we normally stretch out over anywhere from 2 hours to a full day. And one of the things that we do in this workshop is stand up an observability tool. We use an EFK stack. And basically what we do is make sure that our app is instrumented to be capturing the inputs and the outputs of the machine learning model in a meaningful way. So part of what we recommend is that your data scientists actually work with your back-end engineers and your front-end engineers to be capturing the data so that you can get that feedback in real time. Because one of the things that often happens, one of the, I don't want to say pathology because that's too strong of a word, but one of the maybe anti-patterns we see is that we're not actually recording the inputs and outputs going into a machine learning model in a way that makes it easy for data scientists to diagnose the problem. So I think that the existing tools are good enough, but you have to be deliberate about designing your instrumentation.
Okay. Do we have another question in the audience? Yes, I see one in the back.
Hi, thank you for the presentation. How do you deal with concept drift? How do you detect it? How do you react to it?
With concept drift?
Yes.
I'm not actually familiar with that term. Can you?
So with a situation where a model is losing accuracy over time, because yes.
Yeah, okay, yes. So that goes to the observability question, right? Yeah, sort of the shelf life decay of a model is something that I've seen this be a really big problem I've seen this problem actually pose existential threats to businesses. One of the ways that you can go about that is by creating a feedback loop with your observability tools to have another layer on top of sort of your machine learning so that you're actually evaluating that performance and you're monitoring the performance of that model. So one of the slides that we have here is we kind of, I didn't go through it today, but we walk through what a data scientist sort of needs in the process, going through all the stuff. And the last step is just closing that feedback loop from your observability tools and making sure you're linking it to business value. So where data scientists have to talk to back-end engineers and data engineers to make sure that things are implemented right, they also have to be talking to business analysts and to the people tracking how the business is doing, because that's how that manifests. That's where you see that problem first.
So I think we have time for one last question before we take our break. So.
Hi, thank you. So I'd like to play devil's advocate and say that continuous integration for data science is sometimes for some projects a really bad idea because the KPIs become, get out of whack and they don't really represent the thing that you're actually, the business value and so on. But I think we'd probably agree on that, that some project somewhere is bad for continuous integration. So rather I want to ask, how do you differentiate which projects are good for this kind of framework and which projects you wouldn't try that on?
That's very easy. My classifier is just return good. I think that it's good for all of them, but you do bring up a good point, and this is the other hidden slide that we don't have, is that the objective function should actually link to business value and not actually machine learning performance. And so the way that you keep your KPIs, the way that you keep from continuous delivery and deployments schedules from affecting your KPIs is to make sure that what you're measuring actually links to your business value. Because what the sort of side benefits of continuous delivery and continuous integration is that work is shareable, discoverable, you can work more easily in teams, things like that. So those are the other benefits. It's not just about pushing things to production.
Can I just one comment maybe? So this is not always possible because the KPI is always about the past and business value is always in the future. So if there's a really bad signal to noise problem, then you can't, which is often the case, you can't do this.
Yeah, that can be the case, in which that's maybe a little bit of a different question. That's like a business analytics question, I think. Yeah, I mean, that certainly is a risk, but we assume that we can address that problem. But it's a good point.
So always.
My stance will be always, non-dogmatically always.
Okay, so on that positive note, let's give another round of applause for Emily.